Hello, my name is Pannita Suksawas. Today, I will talk about band gap and conductivity mass action low energy band for semiconductors breakdown mechanism. Let's get started. At the topic first, I will talk about band gap and conductivity. I start with how energy bands form and why the band gap controls conductivity. I use the lecture diagram to compare metals and semiconductors, then connect this to carrier statistic, p-interaction behavior, and breakdown. From atoms to bands. When many atoms form a crystal, discrete levels broaden into bands. These few valence band and the usually empty conduction band are separated by Eg. Electrons must be excited across Eg for conduction. In silicon, bonding form sp3 hybrid orbitals, and the bonding antibonding combination group into Bb and Cb, creating the band gap we see here. And next, I will talk about metal versus semiconductors. On the left, metals show overlapping bands. Empty state lie at nearly the same energy as filled state, so electrons move easily to high conductivity. And on the right, semiconductors have Bb and Cb separated by Eg. At 0 K, there are no free carriers. At higher temperature or with light, electrons cross the gap, creating electron-hole pair. And conductivity equation. Quantitatively, conductivity is like this equation. Both electrons and holes contribute increasing carrier concentration N and P by doping or increasing mobility mu. Next, we connect carrier statistic to the band gap and temperature through the mass action law. At equilibrium, the product of electron and hole concentration is a material and temperature dependent constant. You can see this equation, right? For intrinsic material, that N equal to P and equal to Ni, and the Fermi level is near mid-gap. In N-type, donors push EF upwards. NO will amount ND, while PO equal to Ni square divided by Nd. In P-type, acceptors pull EF downward. PO will amount Na and NO equal to Ni square divided by Na. The diagram shows EF shifting, but Eg stay the same. In N-type, donors supply extra electrons. Electrons are majority, hole minority. EF shift toward Ec. In P-type, acceptor create hole are majority, electron minority, and AF shift toward EF. Doping chain NP and EF, but the band gap Eg remains essentially constant. p-n junction forward bias. Forward bias lower the barrier and narrows the depletion region. Electron in the N side diffuse into the P side and recombine. Hole diffuse the other way. The diode current rise exponentially with voltage. The energy band diagram shows EC and EV bending down at the junction and carrier are crossing the reduced barrier. The energy band diagram shows EC and EV bending down at the junction and carrier crossing the reduced barrier. And next, p-n junction reverse bias. Reverse bias raises the barrier and widens the depletion region. Majority carriers are pulled away from the junction. Only a tiny reverse saturation current flows set by thermally generate. Minority carriers swept by the field. The diagram highlights the larger barrier and the small current part. And last, p-n junction, no bias. At equilibrium, with no external bias, diffusion from high to low concentration initially drives carriers, but the built-in electric field opposite it. This balance to form the depletion region with immobile ions and a built-in potential Vb. Net current is 0. Diffusion current equals diff current. Avalanche breakdown. At high reverse voltage, minority carriers accelerate by the strong field collide with lattice atom and create new electrons hole pair. Impact ionization. This chain reaction sharply increase current. We call it avalanche breakdown. Its breakdown voltage increase with temperature because carriers scatter more and need a larger field to gain the same energy. Finally, topic Zener breakdown. This produces a sudden increase at reverse current at the Zener voltage. Unlike avalanche, the Zener breakdown voltage decreased with temperature because band gap narrowing and stronger tunneling occur at higher T. In summary, band structures explain conductivity, carrier SATA. In summary, band structure explain conductivity carrier statistic and give the mass action low doping shifts. The Fermi level p-intention behavior depends on bias and reverse breakdown happens where Zener or avalanche with opposite temperature. Hence, thank you for watching.